First time at this conference, and I find it very interesting, so thank you for giving me the possibility also to speak. So the poster I'm going to present is about stability of perovskite-based solar cell. So what I'm showing in the poster is what we are doing at the University of Rome Tor Vergata, so the CHOSE Center for Hybrid and Organic Solar Energy. In principle, we are investigating two architectures, the Mesoporous architecture that the previous speaker were already presenting, and the Planar structure where we don't use the Mesoporous structure of titanium oxide to realize our device. And we are investigating these two architectures in terms of stability. In the case of the first Mesoporous architecture, we saw already how it is realized, while in the case of the planar structure, we have a very similar structure to what we have for OPV devices. So we use the ITO layer, then the PDOT, the perovskite, the PCBM, the TOX on top, and then we cover it with aluminum. So we did some stability tests on both architecture. For what concerns the planar architecture, we are testing only small area devices because this architecture we just started to study, so we didn't scale up the process, and this is what we get. So we can achieve an efficiency of around 7.5%, but once we start the aging test on the devices, we have a really fast decrease of the efficiency of the device, which is in terms of tenth of hours. So this architecture at the moment is really unstable. For what concerns instead the Mesoporous architecture, actually our goal is to scale up the device, because in our laboratory we concentrated the activity on scaling up of the technology. So we were implementing a process which allows to get efficiency on our device, on a larger device, which is 10.1 square centimeter, of 7.7 in the case of a single step deposition of the perovskite, which means that you start from a solution in which you have both precursors of the perovskite, and then if you move to a double step process, we can achieve 13% efficiency, which is actually the record for a perovskite device at this moment. Here I show also the hysteresis measures, because this is really an issue on such kind of device, and as you see, continuously scanning the device, we have quite good performance in terms of hysteresis. We were characterizing the modules we were realizing, so two parameters were considered. We were checking the ultra-sporting layer, so we were testing a P3HT-based device and a spirometall-based device. As you can see, the efficiency in the case of a P3HT-based device is, the stability is not so good, while for the spirometall-based devices, the system is a bit more stable. In this first experiment, we were considering not encapsulated devices, and for this reason, maybe we also had this fast degradation in the performance of the device themselves. When we moved to, and this sample were realized using a single step deposition of the perovskite. When we moved to double step deposition, we tried to encapsulate with the lamination of material on top of the device, and what we saw actually was that in both cases, so this device is the single step reference device, and this is the double step device. So if you see in both cases, after the lamination, there is a strong decrease in the efficiency, which is actually very high in both cases, but in the case of a single step deposition device, let's say that after the encapsulation, there is a decrease of the efficiency, but then the device is quite stable for quite a long time. While if we move to the double step deposition, we have a decrease after the lamination, and then also after the time during the light soaking system. So this we still have to understand why, since this double step process is still ongoing, the optimization, maybe we have some problems during the deposition of the first film that then somehow gives a problem during the lifetime test. So if you are interested in this topic, please come to poster number 7. I'm there for you. Thank you.
Thank you very much. This talk is by Dr. Ravi Misra from the Ben Gurion University of the Negev, Israel, about concentrated sunlight accelerated testing of perovskite materials.
Good afternoon to all. Let me thank you first for giving me an opportunity to present my work here. My work is on the perovskite material. Actually, Thomas and Professor Hahn and now speaker told all things about the cells. Now we are giving attention towards the stability of material itself. And for the stability of material itself, we did accelerated light stability test, in which we did the testing of material, encapsulated films of material under the concentrated sunlight conditions of 100 suns. And in this, we have used the material of methylammonium lead iodide and bromide. So our main motive of this study was to screen the material which we can use for our studies, which is sustainable for high temperature, high concentrated conditions, sun conditions. And second motto was to test the material under the accelerated testing conditions, so that we can get the results in less time duration about the stability of the material. In this, you can see that the material was exposed with our solar concentrator, in which we are having the facility to get the concentrated sunlight towards the material through optical fiber. As Professor Eugene told you yesterday that we are having that facility, and he explained about that facility. We used that concentrated sunlight to expose the sun, to expose the material, our films, and after the exposure, we can get the results, and we can see that when the material was placed at the 5 degrees C, and in this condition, we know from our previous experience with the in different paper, which is here referred here also, that in this condition, the temperature of film, which film field can get up to 25 degrees. And we can see that in 1 hour of continuous exposure with the 100 concentrated sunlight, we cannot get any type of degradation here. But when we change the temperature from 5 degree to 25 degree of the platform, means we are changing the temperature of platform from 5 to 25 degree, and the material field temperature is changing from 25 degree to 45 to 55 degrees centigrade. And in this case, we can observe that in only 20 minutes, we can get the degradation of materials, and it is increasing with the time, and we can get the complete degradation in UV absorption spectra. So we can say with the help of this that the material is degrading under the concentrated sunlight, but only concentrated sunlight is not sufficient to degrade the material. It needs elevated temperature also. And we also calculated the absorbed solar photons number at different spectras, and we can get the degradation clearly here. Another study we did that on elevated temperature, when we did the stability studies, we thought that maybe this is the effect of temperature. So if it is the effect of temperature only, then it should not be degraded at more elevated temperature in absence of light. So we did dark annealing here, and you can see the results of dark annealing, that with the annealing at 25, 35, 55 and 75 degree for an hour, we are increasing, we can see a small increase in the absorption of material. So then we went for the XRD studies of the material, and it is the XRD studies of methylammonium lead iodide, and this is the lead iodide, pristine lead iodide itself, and we can clearly see that here our material is degrading from methylammonium lead iodide to lead iodide, and we can see the characteristics peaks of lead iodide here, here and here, which can be assigned to the lead iodide. The same studies when we did for the methylammonium lead bromide material, then we can see that at any temperature, whether at 5 degree or elevated temperature of 25 degree, means material can reach at 45 to 55 degree, there is no degradation. So from these studies, we can conclude that photobleaching of methylammonium lead iodide films was observed after their exposure to 100 suns for 60 minutes at elevated temperature conditions due to the decomposition of material from methylammonium lead iodide to lead iodide, hexagonal structure of lead iodide, and there is no any degradation was observed when the temperature was 25 degree, whether we exposed with the concentrated sunlight. So we can say on the basis of this that the material can degrade from methylammonium lead iodide to lead iodide in well encapsulated state, but it is the temperature dependent phenomena under concentrated sunlight, means temperature can play important role in this, and in the same stress conditions methylammonium lead bromide films were more stable. This is the conclusion, and if you are interested in this, you can ask any questions in poster, and poster number is 8, so you are welcome for that. Thanks.
And will be done by Gisele Binator.
Good afternoon. As I was presented, my name is Gisele, and I'm a PhD student in DTU. And I will present this work that it's a conclusion of how to make reliable stability tests using the ISOS conditions, the ISOS standards. And as some years ago, this group replaces ITO with silver-based modules, where you use silver in the electrodes. And now for the future, and it's being developed, some modules that don't use silver at all, we are replacing it with carbon. So these kind of modules, they are even more environmental friendly, and they can even be thrown in the normal bin, so it's much feasible for wider disclosure in the widely spread in the world. So you have a really low impact of these modules. And as you see in the presentation from Professor Krebs yesterday, we do a row-to-row deposition of production of the solar cells. And 100 meters of our row provide us around 2,000 of these modules, as you see in the pictures, and as I have one here. These postcard size modules. And as the processing is very reproducible, we choose 80 cells to be tested in stability tests. And these 80 cells were separated in 5 ISOS conditions, and they were tested in 2 laboratories here in DTU, in Roskilde campus, and in a laboratory that we have collaborations in Aalborg, in the very north of Denmark. And these are all the results. We choose the tests D1, D2, D3. They are the dark tests outside and light. And we'll describe a little bit in details here. In the dark test is the black line here. They are, all, as expected, very stable. In the D2 test, that is the dark heat test, they are both the red lines here. The dark red, there are these here, are developed for laboratory 1, and these that had a drop here were made for laboratory 2. There is a little bit light red. And here, as expected too, we got a very stable solar cells here. There is 8, as each test has 8 cells, 8 modules. All 8 are very stable from the beginning until the day 35 that we settle the limit for this test. And for laboratory 2, we saw that there is some experimental problems here, since it come back to close to the original efficiency, and also because all the modules go more or less the same way, so it was clear to see because of the amount of the solar cells of the modules in this case. For the dark dump heat, that is the D3 test, the light green is for laboratory 2, the dark green is for laboratory 1, and both of them follow, they are over each other. So this is the importance of following the standards, since they are very similar results of similar modules. Remember that all the modules were chosen in all parameters, VOC, fill factor, efficiency, current, all the factors were very similar. For outside tests, O1, we have for laboratory 2, these curves, all the modules going the same way. For laboratory 1, the darker blue. And here, of course, is outside tests, so you have different weather in both of the places. And they are following a smooth degradation in laboratory 1 and a little bit more accentuated degradation in laboratory 2. And for laboratory lab 1, L1 test, ISOS, that is the light test. For laboratory 2, we saw also that there is some measurements problems here. The modules don't follow a pattern. In these days, it was the same day that there was some problems here in the D2 measurements. In comparison, in laboratory 1, we have here most of the solar cells going in a way, and we have 3 solar cells that correspond. There is 2 here and 1 here that degrade less faster than the others. Then we started to see what it was happening here, and when we checked the temperature on these 3 cells were about 5 degrees less than the others. And then, since it's L1, there is no control of the temperature there. So here is really call our attention about how the temperature affects on this test. And we could only see, because they are very similar in the beginning, and they were submitted to the same ISOS test. So this work is an overview about the importance of these ISO standards, and we come to the conclusion that at least 4 very similar solar cells, if it's possible to have them, are very will increase much more the reliability of your tests. We recommend from 4 to 10. That would be a very nice number. If you want to see more details about this burning phase, and to see separately all the tests, more details, but details too about the production of solar cells, I will be available in the poster section, poster number 9. Thank you very much.
Lee from Imperial College, London, and it's about degradation of morphology in OPV. Do we have a speaker? Monica. Okay. So, good news. I'm sorry. This is my mistake. It's not okay. It's not good news. Now it's it's Yannick Zimmerman, and the talk is degrading OPV, poison and environmental risk. Sorry.
Here. Okay. So welcome to poster number 10. If you're interested, you're welcome to come by in poster number 10. And I also refer to my supervisor, Dr. Markus Lenz, who will give a talk at 2 o'clock, which is about the same topic. We at the University of Applied Sciences and Arts Northwestern Switzerland, which is in Basel, we are also interested in OPV, which are degrading, but not in the actual mechanism, but in the effects it might have to the environment. So we want to see, when OPV are degrading outside, for example, whether this might be any risk to the environment in the future. And we want to assess this at a very early stage of development, so that we can exclude any risk if OPV in future will go into large-scale production. What we did, for example, is we took OPV and, as a comparison, CIGS cells, and we exposed them to different environmental waters in order to see whether they are degrading or not. So we cut them actually into cell fragments, as you can see here, which is simulating a really, really worst-case scenario. So which might happen on a landfill, for example, or when you put OPV on a roof and it's mechanically degraded by hail, for example. And after a few months of exposure to different kind of waters, they look like that. And even from looking at that, you can see that some of the components are actually leaching and would end up in the environment. So from these metals which are leaching from OPV and CIGS cells, we were then calculating an environmental model to see, for example, in a rooftop acidic rain runoff scenario, what kind of predicted environmental concentrations we can expect in the environment afterwards. One result was that from OPV, some silver and zinc was leaching, but in concentrations for the environment, which were, for example, at least 1 magnitude of order below World Health Organization drinking water limits. So you can even drink that water if you want. And these concentrations were as well clearly below toxic levels for aquatic organisms, which is a good result. On the other hand, for example, CIGS cells, molybdenum, cadmium, and here as well selenium were leaching, and we would expect concentrations in the environment which are above these drinking water limits, about the WHO. And in the case of cadmium, the concentrations were actually even above toxic levels for certain aquatic model organisms. So CIGS cells might indeed be in this worst case scenario, a danger to the environment. Then we did another leaching experiment, but not this worst case scenario, so not by cutting them into pieces, but we took entire PV modules and we irradiated them in a sunlight simulator for 1 year outdoor sunlight conditions, and then did some bending. And what we were able to see is that in the CIGS cells, some clear cracks were forming, whereas the OPV encapsulation foil were actually still very flexible and no cracks were visible. You can see them on the one hand by light microscopic analysis, and the other hand we have a technique with an optical white light sensor which allows us to characterize the cracks, like the number of cracks per area and the depths of the cracks. And in this scenario we were able to see that because the OPV encapsulation layer was still highly flexible, no ingredients or no components were actually leaching, whereas from the CIGS cells some zinc was leaching from the top functional layer. So to sum up, so far what we know is that OPV really seems like to be a safe product and no danger to the environment, whereas from CIGS cells, some metals might be a problem to the environment in the worst case scenario. Post number 10 if you want to have some further details. Thank you.
Next try. The next topic, the next talk is again from Roskilde, and it's done by Frederick Nehm, and it's high barrier investigation in different climates and diffusion coefficient dependencies on temperature and humidity.
Thank you. I'm Frederick Nehm. I'm actually from AAPP in Dresden, led by Professor Leo, and I'm working at the moment, I'm doing my PhD on barriers and encapsulation of organic devices. And please let me start out my motivation by saying we are not living in 2050 land, by which I mean, of course, if you put your OPV cells in outdoor conditions, they're not going to be standard conditions, and they're certainly not going to be stable, constant conditions. So they're going to change. And if you want to know your lifetime of your device, you might want to consider different climates and WVTRs as well, for that matter. So so far, WVTR recalculations, so water vapor transmission rates, recalculations are rather difficult because of a lack of in-depth analysis of different climates to high barriers or solar cells. So what Lars has told you yesterday is that in Dresden we have a nice setup of an electrical calcium test, which is very versatile. You have in parallel more than 60 samples, which can be addressed individually with different climates. And we've done a WVTR matrix from 20 to 68 degrees centigrade and 0 to 90% relative humidity. And with this, we want to help to shed some light on how WVTRs accelerate over different climates, as you can see. Yeah, okay. So this is basically already the heart of the investigation. We have ZTO, zinc tin oxide barrier on a 75 micron PET foil from the Fraunhofer FEP from John Falteich. Some of you might know him actually. And you have the WVTR on the Y scale and the relative humidity on the x-axis. And what you can see is that we have here three nice graphs with data points for 20, 38, and 60 degrees centigrade. And we were able to fit these data points very nicely, actually, with a linear model. So we can already say that for this kind of barrier, we are expecting absorption coefficients which are very much in terms of Henry's law. So the outside concentration of air is directly proportional, linearly proportional to the inside water concentration inside the test. Okay. But of course, we didn't stop here. We went a lot further, which I would be delighted to discuss with you at the paper. It's at the poster number 11 actually. We've looked at different sorption models and temperature effects, which we found out over the WTRs of the substrate itself. We saw that there's some change in the barrier layer itself, independent of the substrate above somewhat 40 degrees centigrade. We've tested the barriers in inverse geometry, which means that we have the ZTO facing the humid air directly, and saw a very big offset there. And we have done some fitting routines for the transient regimes before the calcium test reached the steady state behavior, and we could extract some diffusion coefficients and concentrations of water inside the barriers inside the calcium test. So if any of you would like to discuss either these results or even anything related to barriers, encapsulation, or the calcium test, I would be happy to see you at the poster. Thank you.
And the last talk by Alberto Gregory from France about the delamination in OPV devices.
I would like to thank the organization to allow me to present the poster in front of all of you. And I'm a PhD student at the University of Po, and part of my thesis work is investigating the mechanical properties of OPV devices. In the framework of my thesis, I developed a test to find the weakest mechanical point in OPV. I worked on inverted geometry devices, and what I've developed is a setup for a pull of force test. So it's a tensile stress. I started from a tuck test that is meant for soft pressure sensitive adhesive that allow me to have a good control on many parameters like the surface which I test, the contact pressure, the contact time, and the pulling speed. I started developing the test using standard P3HT PCBM cells with traditional classical water-based P.PSS, and then I moved to other active layer and to another P.PSS dispersion in organic solvent developed by one of the partner of my project at Ereus, Dr. Stefan Schumann. And we can see that as the output of the test, there is for P3HT PCBM, there is an improvement in the adhesion. For a second polymer, PSB TBT, there is a slight improvement, and for the third one, PDT STZTZ, doesn't change a lot. It's comparable. As output of the test, we have seen difference in adhesion, but why? So we investigate the surface to see if it's if there was any difference in the failure path, in the fracture path. So we used the AFM to investigate the topography of the two surfaces, and XPS made by another partner of the thesis at Universitat of Tübingen. And we see that on the lower part, in both cases, we have only active layer, so P3HT PCBM, while in the upper part, in the case of HTL water-based, we have only HTL, and so we guess that the fracture follow more or less the interface between active layer and P.PSS, while with the new organic solvents dispersion, we have both P.PSS and P3HT-PCBM. So we think that the fracture moved somewhere in the active layer, still close to the interface. That could be, that introduce a sort of cohesive degree in the fracture that could explain the improved adhesion. So if you want to know anything more, I will be at poster number 12 to answer your question. Thank you very much.
Thank you.